Hey there, it's Aaron here. I'm going to show you how to do problem 2.2.1.8 in our homework with sequences and series. It is asking us to express S sub n as a telescoping sum, find out if it's convergent or divergent, and if it is convergent, to find the sum. So, the first thing that we're going to do is we're going to take this guy and we're going to decompose this into partial fractions. All right, let's go ahead and jump right into that. So we're going to factor the bottom out. It's going to be 2 over n plus 1 n minus 1. And that's going to equal some number a over n plus 1 plus some number b over n minus 1. We're going to multiply everything by n squared minus 1, or n plus 1, n minus 1, and we'll be left with 2 equals a times n minus 1 plus b times n plus 1. Perfect. Let's go ahead and plug in n equals 1 to cancel this out. If n equals 1, we're going to have 2 equals b times 2. So b is therefore 2 over 2, which is 1. Perfect. And now if we plug in n equals negative 1, that's going to cancel out, and we'll have 2 equals a times negative 2. A is therefore negative 2 over 2, or 2 over negative 2, which is negative 1. Awesome. Quick, easy, really nice. So this is equaling negative 1 over n plus 1 plus 1 over n minus 1. Awesome. Now this is going to really help us out in showing the telescoping series. Because if we just wrote everything out, if we wrote out the partial sums using this guy up here, it wouldn't really allow us to cancel anything out. And as you'll see in a few seconds with this right here, this method, you can cancel some really cool stuff out. So I'm going to go ahead and put purple around this because that's really awesome, and I love purple. Who doesn't? So I'm going to go ahead and I'm going to start at small n equals 2, and I'm going to take the partial sum of n equals 2, and I'm going to go all the way to 6. So for n equals 2, I'm literally plugging in 2 into small n. So I'm going to get negative 1 over 2 plus 1 plus 1 over 2 minus 1. And for n equal 3, I'm going to have negative 1 over 3 plus 1 plus 1 over 3 minus 1. At n equals 4, I'm going to have negative 1 over 4 plus 1 plus 1 over 4 minus 1, and so on and so forth. All right, negative 1 over 5 plus 1 plus 1 over 5 minus 1, negative 1 over 6 plus 1. Wow, that was a weird parenthesis. There we go, that's better. Plus 1 over 6 minus 1. Awesome. Now that looks a little weird, so we're just going to go ahead and evaluate the bottom. So this is 3, this is 1, that's just 1, 4, 2, 5, 3. You'll probably notice a pattern here. Oops. 6, 4, 7, 5. Awesome. Now, if you haven't noticed already, there are some things that will cancel out, and this is going to make our lives a lot easier. So, red for cancel, because red always does that. So, we have a negative 1/3 here, and we have a positive 1/3 here. And when you add those up, they go bye-bye. Oh, oops. There we go. And we also have a negative 1/4 here, and a positive 1/4 here, and we have a negative 1/5 here, and a positive 1/5 here. Now, if we are taking n to infinity, we're just going to go until the largest number possible and then keep going for this n, right? So we're not really worried about 2 and 3 and 4 and 5. We're more worried about like 10 million, 20 bajillion, whatever, right? So if we're going to infinity, these two numbers will always be here. They'll always be here. And everything else beyond these two numbers will end up canceling out all the way through until we get to, you know, for whatever term you'll have, like let's say n equals 5,000. You'll have this one for 5,000 and you'll have this guy for 4,999. So we're going to rewrite this. We're going to say that partial sum, oops, I don't like red for that. Let's go with green. Perfect. We're going to say partial sum, where n is 6, is going to be equal to 1 plus 1/2, which is 3/2, plus, what is this? This is -1 over n. And then this is -1 over n plus 1. Yeah, you see what I did there? Oh, that was a little weird one. There we go. Yes. So that is really cool, and that's awesome, and you need to remember that. So basically, I'll show you what I did here. These two are going to come down like that, and they're going to get added together. And then this guy comes over here, and this guy comes right there. Perfect. I know that looks messy, but you get what I mean. Okay. So now what we're going to do is we're going to go ahead and go back to the original statement, right? Let me change colors for this. We'll change back to blue. So the limit, and we're gonna call this big N because we're choosing some number big N. It's really big. As it goes to infinity, of the sum, where small n equals 2, all the way up to that big N, right? The limit is going to be, or the limit of the sum of this particular pattern, and I'm going to write the decomposed version because that's the one that we're working with, and that's the one that really matters, right? We could go back up here and write this original one, but it doesn't really do much for us. So the limit as big N approaches infinity from small n equals 2 in here all the way up to that big N, right? That's going to be equal to the limit as big N approaches infinity of the partial sum, which is going to be 3/2. And I'm going to go ahead and change that to a negative, and that's going to be a negative. It's going to be 3/2 minus 1 over, we're plugging big N in there, remember? Minus 1 over big N plus 1. Awesome. Now we can definitely evaluate that limit. And as we know, anything where we plug infinity in the bottom of a fraction, it's going to go to 0. And if we plug infinity into the bottom of this fraction, it's still going to go to 0 because infinity plus 1 is still infinity. But notice right here that you can't plug infinity anywhere in there. It is simply 3/2. So the limit as big N approaches infinity of 3/2 is, I'm going to go ahead and write that. Oh man, I'm starting to write in red again. Whatever, it's fine. Of 3/2 simply equals 3/2. And so for any partial sum that is bigger than n equals 3, we're going to have this pattern of 3/2. And since we're taking the limit to infinity, we're not really worried about the smaller numbers anyway, as I said before. So the answer is 3/2. Now, how do we know whether this converges or diverges? Well, if the sum was, say, infinity or negative infinity, that really wouldn't be nice, would it? It's not really going anywhere. It's going either infinitely up or infinitely down. And so the series has this number, so it must converge. And that's it.